Sorry, I'm trying to pick different music. Give me a second.
You know I want you. It's not a secret I try to hide. I know you want me, so don't keep saying our hands are tied. You claim it's not in the cards. Fate is pulling you miles away and out of reach from me. But you're here in my heart, so who can stop me if I decide that you're my destiny? What if we rewrite the stars? Say you were made to be mine. Nothing could keep us apart. You'd be the one I was meant to find. It's up to you, and it's up to me. No one can say what we get to be. So why don't we rewrite the stars? Maybe the world could be ours tonight.
You think it's easy. You think I don't wanna run to you, but there are mountains and there are doors that we can't walk through. I know you're wondering why, because we're able to be just you and me within these walls. But when we go outside, you're gonna wake up and see that it was hopeless after all. No one can rewrite the stars. How can you say you're mine? Everything keeps us apart, and I'm not the one you were meant to find. It's not up to you, it's not up to me. When everyone tells us what we can be, how can we rewrite the stars? Say that the world can be ours tonight.
All I want is to fly with you. All I want is to fall with you. So just give me all of you.
It feels impossible.
It's not impossible.
Is it possible?
Say that it's possible. How do we rewrite the stars? Say you were made to be mine. Nothing can keep us apart, 'cause you are the one I was meant to find. It's up to you, and it's up to me. No one can say what we get to be. Why don't we rewrite the stars? Changing the world to be ours.
You know I want you. It's not a secret I tried to hide, but I can't have you. We're bound to break and my hands are tied.
So, Oogway, this was the one destined to stop me?
A big, fat panda who treats it like a joke.
Oh, do you actually believe this is the warrior destined to defeat me?
You? Him? He's a panda. You're a panda.
You're a disgrace to Kung Fu, and if you have any respect for who we are and what we do, you will be gone by morning.
Then why didn't you quit? You knew I was trying to get rid of you, yet you stayed.
I stayed. I stayed because every time you threw a brick at my head or said I smelled, it hurt. But it could never hurt more than it did every day of my life just being me. I probably sucked more today than anyone in the history of Kung Fu, in the history of China, in the history of sake.
Probably.
I stayed because I thought if anyone could change me, could make me not me, it was you.
Look, it's the Dragon Warrior.
They totally hate me.
Totally.
How's Shifu ever gonna turn me into the Dragon Warrior?
I'm surprised you remember so little. But you were so little when it happened.
You think knowing will heal you? Huh? Fill some crater in your soul.
Stay down.
I have to get to him.
Then tell me why.
Here's your answer. Your parents didn't love you.
He was there, okay? The peacock was there the last time I saw my parents. He knows what happened, where I came from, who I am.
Is this my mom?
Your story may not have such a happy beginning.
But that doesn't make you who you are.
Look how it turned out. You got me, you got Kung Fu, and you got noodles.
It is the rest of your story. Who you choose to be.
Huh?
You are too concerned with what was and what will be.
To make something special, you just have to believe it's special.
There's a saying. Yesterday is history. Tomorrow is a mystery. But today is a gift. That is why it is called the present.
There is no secret ingredient.
It's nothing.
It's just you.
What?
is no secret ingredient.
Do you want to learn Kung Fu?
Why can't you follow the simplest orders?
I can't stop myself. I see a dragon and I have to just kill it, you know? It's who I am, Dad. Oh, for the love of it, I was a coward. I was weak. I wouldn't kill a dragon.
Even as a boy, I knew what I was, what I had to become.
No one just gets as good as you.
You know what I just remembered? I know why this won't work. The problem is, okay, hold on. I need to demonstrate this because this is something really stupid. I'm gonna try and fix later today, in a little bit. I just remembered this. Let's say that 5 is greater than 4, right? And then let's say what info 5 is greater than 4. This, I'm pretty sure, if I remember correctly, will just, it'll output nothing. And if we have an else branch, right, and we say info, just do 2 and 1, right? So if it's greater, oh, I'm missing that. See, nothing, but as soon as we flip it, we get 2. So it's kind of weird. And even, so let's say that we add it to a variable, so have x, that's s, x, and then we say let's do return x is equal to 1, and then return x is equal to 2, right? And then we just do info x. This would return true when, so instead of, oh, what did I do wrong? Can't return from top level code. Oh, we don't need to return, we can just set it. We get nil, which is super weird. So there's something wrong in the code that I have to go through and fix that I don't feel like doing right now. So that's a problem here, which is a slight problem. So that's something I have to go through and fix. I forgot that was an issue. That's what I'm going to do. That's what I'm looking at right now. I never used the close formula. I've always, I only ever learned of the recursive one. Towards the bottom. Alright. That's not closed? Oh. Interesting. Matrices form? Closed form of the Fibonacci sequence. This looks like the recursive. Closed form solution of Fibonacci-like sequence. So we have our nth term, 1 plus the square root of 3. To the nth power, it looks like 1 minus the square root of 3 to the nth power divided by 2 to the square root of 3. Okay. I'm gonna have to do more research on this because I've never used the closed one, so I don't know if I'm looking at the right one. So as with the Fibonacci numbers, closed form is, so we have f of at the end term is equal to 1 plus square root of 3 to the nth power minus 1 minus divided by 2 to the square root of 3. Directly corresponding. Sorry, I didn't see you started a call.
You're good. What's up?
Nothing much.
Dude, you were. I'm not gonna lie. You had me so aggravated as I was trying to. You missed the formula. You just went right past it.
Oh fuck. Okay, let me go back.
Second. Here, let me share my screen because I'm like, I'm not watching the thing.
Yeah, no, you're good. I've never had to use, or I've never learned what the closed form is, so...
Yeah, in Discrete, which is like a proofs class, you learn how to prove the closed formula.
Okay.
But, also, those aren't matrices.
Oh.
That's a combinatorics notation.
What
so
is...
the top number, if you see like 5, for example, if you see 5 over 4 in a parenthesis, that means 5 choose 4. It's saying in a group of 5 elements, how many ways are there? How many combinations are there? Such that you get 4, you know, so if you have 5 people, how many ways can you line up 4 of them? So it's a combinatorics thing.
That's something that I've never learned.
Well,
okay.
Yeah, it's notation you'll see for Pascal's triangle, which is like, say I give you I say write x to the 15th, x plus 2y to the 15th. You can actually like, there's a formula for it, and it's that. But anyway, let me fib closed formula.
That's something new.
Oh yeah, it's a real hoot. Here we go. So can you see
Oh yeah. Okay.
This is the formula right here. So the other ones weren't closed because it said f of n minus 1, right? Like you had to know a previous term.
Yeah.
Here, you just need to know a number, n. And this is the formula. 1 over the square root of 5 times 1 plus, right, all of that shit, to the n power. So if I want to know the 200th term, I don't have to know the 199th, the one, you know, etc. So this is the closed formula. In fact, if you go on here, I think here it just proves it. Yeah, if I recall.
That is... I've never seen that before. That is that is weird. Oh my god.
So here we get it as... Where is it? Oh, yeah, right here. So here it would be in code, like that.
Oh, that is weird. Okay.
Yeah, it's you're like, why the fuck is there a 1 over the square root of 5 everywhere?
Yeah, that is a little confusing. Why is that? Is there a reason for it? Obviously, there's a reason for it because it's being used like that.
Well, in the proof, it's just no one can really figure it out on their own. It was one of those ones we had to, like, you know, have like, what the hell, why?
Okay.
It's basically just you dick around with the algebra long enough, you get to something that looks like this.
Well, that is, that's something else.
Yeah.
That's confusing as hell. Okay.
But anyway, yeah, there you go. Now you know. Since you don't want it, since you can't do the if check if you want, or if you ever want to do, there's a lot of formulas for like recursion, like without recursion. Like a whole part of the class is taking, how do you take a recursive formula? Because almost all recursive formulas have a closed formula where you don't need to do recursion.
Okay.
So, but anyway, this is that one. So I figured if you wanted, it's the fastest approach typically because, you know, you don't need to do any recursion, no memory. You just compute this, some, one iteration, and you get it. But I was thinking that would be a cool idea for a function. If you also ever want some good like functions, look at Math.js.
Math.js? Let me look that up right now.
So Math.js allows you to, for example, I think it's really cool. You could do something like this. Like you can type in something like
Ooh.
You can do docs. There we go. Like you could say parsing and evaluation. You could say 2 inch to centimeter, and it'll convert it. Or what's really cool is you can pass in a mathematical expression like, you know, like there's simplification. I gotta find it. Examples. Basic, big numbers, complex, angle, advanced, crap. Okay, well I can't find it, but basically you can pass algebra, right? Simplifying expressions. You can pass in 3 plus 2 over 4 and it'll simplify it. Or you can pass in something like x times y times negative x over that and it'll simplify it to just negative y.
Oh, that's interesting. Okay.
Because it under the hood will build an AST, right? For these mathematical expressions. And there's certain rules you can use. In fact, this is actually the coolest thing I think I've ever built. I'm not gonna lie, I'm so proud of it. Even though it doesn't do all these rules. For a project, for one of my classes this semester, it's Boolean algebra, which is like it's logic. It's called propositional. It's logic with just logic math.
Okay.
But I built a tool. Let's find it. Which takes in Boolean algebra, which takes in algebraic expressions, like using Boolean algebra, and it simplifies them using like different laws and stuff. And it's cool because it has like simplification with negation laws and like let's say expression. But like basically, I built a little AST for this. A little thing. I'm trying to find the testing file. Here it is. Right? And I could test these. I could type in something like testing what is the opposite of 1? Well, it'll be 0. Or what is the opposite of x and y? Well, it's opposite of x or opposite of y. Or like what is not x? What is not, and it'll like simplify these laws.
Oh, that's cool.
But it's something I wish I could extend, but I'm not big brain enough to like take it past I implemented like the most famous law of them all and then said cool, I'm done.
That's reasonable.
But yeah, if you ever want cool idea, like there's a lot of cool things. Like I really wish I had the time because like this is a project of its own, you know. But I think it would be cool to have like in the math library like an algebra simplifier function or like something that can do like basic like linear algebra and also like Fibonacci, like whatever. But what it would be cool is if like derivatives.
Okay.
One, because when you're in calc, it'll be fun to just punch those in,
Yeah, that would be really easy.
And like sums, you do a lot of that stuff too. So like just having a function which is just a for loop, really, but like having it so you can plug in like x squared and then like sum from 0 to 100, right?
Yeah.
Kind of. So anyway, but yeah, I want to show you that one because you were like, I was like, dude, you went right past it.
Yeah. I'm actually gonna try and find that website so I can see if I can get it.
Yeah, I'll paste it back and.
I got the formula. I found it.
Oh, cool.
That's so weird to look at.
Yeah, it's a fucked equation.
So,
I mean, it's not even the worst, but it's pretty bad.
So the first part is being multiplied by 1 divided by the square root of 5.
Yep.
And then you
do 1 plus root 5 over 2 to the nth power.
The hell?
Yeah.
Like I did pre-cal and this is confusing the fuck out of me. That's weird, but it makes sense at the same time. I don't know.
Yeah, the thing is, it's like, where are these root 5s coming from?
I think that's what's confusing me the most out of it is where the fuck those are popping up from.
Yeah, well, there's like, oh, you're actually right. They did actually do this using matrix stuff. I don't know why they did the parentheses though. I hate this because this is matrix notation.
Yeah.
But this right here has 2 different notations. It's a 1x2 matrix, or it's from 0 elements. How many ways are there to choose 1, which is 0. So it's like.
That's weird.
But if you want a simple function that would be kind of cool and isn't in many languages, implement the permutation.
Permutation? What is that?
Which is P of, here's the closed formula for the permutation function. So what it takes in is, it's like, what if I ask you this, right? How many ways are there to make 4-digit license plates, given that you can't repeat a character, right? And you have, let's say you can only do numbers, right?
Mm-hmm.
How many ways are there to create 4-digit license plates, given that you can only use 0 through 9 and you can't duplicate numbers? That's a permutation, right? You have 9 possibilities for your first spot, right?
Yeah.
But then you only have 8 possibilities for your second spot. 7, 6. It's not 9 factorial, right? That would be if there was 9 possibilities in 9 spots, it'd be 9 factorial. This is 9 factorial over 9 minus 4, so 6 factorial, which cancels out to being a permutation. So that's a simple function, but like it comes up all over the place in like statistics and crap. Oh, and here's the combination function. So and choose R.
What? Is that a matrix or is that what you were saying
No,
before?
these are not. This is, now we're back in the land of logic.
Okay.
So if I asked you how many ways are there, given a group of 3 people, to choose 2 of them.
Okay.
Right? You have like A and B, A and C, B and A, B and... Oh, actually, B and A would count, right? Those 2 are the same.
Yeah.
But if I asked you how many ways are there to line up 2 people in a group of 3, that's a different question. Because order matters. Anyway, I'm not going to bore you with that.
Well, I find it interesting. It's just kind of hard for me to wrap my head around because the highest level of math I've taken so far is pre-calculus. And next year I'll be taking Calc 1 for my first semester in college.
Yeah, and like honestly, it's not hard. It's just there's a lot of it's different. Like there's also the Pascal's triangle, which is, if you've ever heard of this is kind of cool. I've only got to use it once and show off to people in Calc. Binomial expansion. Here's that ugly ass formula, by the way.
That's something. Okay.
Yeah. You'll notice this notation.
Yeah. I keep thinking it's matrices because I just got finished, I think like last week learning, or like 2 weeks ago learning about matrices, and that was our notation for it, was using parentheses. Even though when I was writing my own program for it, it was brackets, which made more sense.
I hate that sometimes it's brackets, sometimes it's this. The good news is you won't really ever see both of them together.
That's nice.
Because the one form of math is discrete math, where you're dealing with like countable quantities and such. Well, when you're dealing with matrices, you're dealing with continuous math, like calculus, linear algebra. That's all math that's continuous. Trigonometry, because there's an infinite number of points between 0 and 1, and there's an infinite number of points between 0.1 and 1, and like you get the idea, right? But with discrete mathematics, you're counting. There's not an infinite number of points between 0 and 1. There's nothing. There's 0, there's 1, there's 2, there's 3. Sometimes there's not even negatives, right? Like, it's, I don't know, it's, anyway, I'm gonna stop. But this is like, yeah, you'll see these. They're not hard. This is Pascal's triangle, but using this triangle, you can like literally, if I asked you like here, oh my god, wow, blur image. Here we go, right? If you've ever done a plus b squared, there's actually a way that you can memorize up to really as far as you wanted. It would be pretty hard to go past 4, but here's the 4th one.
Oh, jeez.
And fascinatingly enough, it creates the exact terms. It's actually kind of cool. It's x to the 8th. So if I said, what is z plus y to the 8th power? What's really cool is you can do this 100% with this triangle instantaneously. If I said, so this is to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th power right here.
Yeah.
Oh no, this is 7th. What you do is you say, okay, well it's z to the 1st power plus z to the 8th power, or 7th, right, because we're doing 7, plus z to the 6th power, 7z to the 6th power plus, and then like, times y. plus 7 or 21z to the 5th power. It goes down.
Yep.
So z will go down by 1 each time, while y goes up, and then the coefficient is this number.
Yeah, I remember doing that in pre-cal.
Okay, yeah. So like you'll actually learn about what's called the hockey stick theorem, which is like a way that it's a theorem that counts the diagonals here, and it's common in like a lot of proofs. So stuff like that. There's like if 100 mathematicians go to a math conference and they all want to shake each other's hands, how many possible handshakes occurred, or is it possible for each of them to shake 5 handshakes or whatever, right? Shit like that.
Alright. That sounds like fun.
Yeah, she is. It was honestly my favorite class. Hardest, but favorite.
Ah. Yeah. I just finished high school, so that'll be fun.
No, yeah. Trig kind of sucks. Depends who you have, I guess. Trig isn't like the hardest, but there's just a lot of like it's Trig, you know?
Yeah.
Kind of boring. Let's see. I recently just reinstalled Windows, and I'm kind of having issues getting like things set up the way I want. So I was able to get like, I don't know. I'm debating if I now want to reinstall like Ubuntu or something.
the constant switch.
Yeah, like here I have WSL with Ubuntu, which is great. I have, Cargo, I have Golang, I have Dino, I have Node, right? I have all of this stuff that I use. I have Make, GCC, all that good stuff. But then the second I like yeet out of that terminal and I go into Windows lands, I don't have Go, I don't have Make. Why Make? Because I did that. But like I'm having an issue getting the versions synced up, Because the issue is it's all fun and games to just use WSL, but the second I want to build for Windows, right? I can't just compile it using the Linux, stuff. So like, I don't know. I'm. But then like, but I would have the same issue if I was just on Linux. But like, I don't know. I have no clue. Right now. I was gonna come on and debate reinstalling or installing Linux and I don't know. I've always used Fedora. I still have Fedora as a second boot, but I kind of want to try Ubuntu as I haven't used it like ever, other than in WSL.
My favorite one when I was using Linux for a little bit before I had several kernel crashes and just didn't want to deal with that was Arch Linux. I liked using Arch. It was a bit of a pain to set up to begin with, but once I got it set up, it was a lot of fun to use, except when there was kernel panics and all that BS.
And that's what I'm like,
shit was not fun.
Like there's Ubuntu. Okay, I'm sorry, 23. There's what is it? I've also never tried Mint.
Linux Mint, it's all right. It's like if Linux and Windows were kind of like combined almost. It had like the back end of a Linux system, but the UI was kind of designed like Windows, if that makes sense.
That's what I've seen. Is it's very like, I don't know, but like the other thing is it's like I know if I just go with Ubuntu, it's like the most supported basically because of this the OS under the hood, but like pretty good things about Mint at the same time.
Yeah.
I'm trying to remember what Mint's based off of.
I think Mint, if I remember correctly, I want to say is based off of actually I don't remember.
Debian. Oh. Well, it's based off Ubuntu, which is based off Debian, so that's actually good to know. Yeah, I'm like, I don't know. I could use. Yeah, GNOME, so it is.
I think that's correct. Info 10. Oh, shit. Oh, wow, that is really fast. Holy crap. Whoa.
Are you doing the,
Yeah. Hold on, I'll send you the syntax, what I did for it. I did the exact same thing, but the syntax looks a bit weird. I didn't send that in a code snippet. Oh, that's gonna be a pain in the ass to read. Hold on.
Yeah, pretty much. Yeah.
That's cool though. Holy crap.
Yeah. Yeah. So there's a lot of for example.
Oh shit, that's fast as hell.
If you can find a formula that's recursive and make it close, that's why you can get some insane speed improvements. And it's interesting now that you've been kind of brought into the world of compiler and like design and stuff, right? You can kind of see why recursive functions are going to be slower than iterative ones.
Yeah.
Right. When you have to create a closure, you have to allocate stuff on the stack. You have to create closures, which means module resolution at runtime. Right. You had to dynamically allocate extra memory. While with an iterative approach, if done right, you already know the stack in that loop every time. Therefore, you're not creating new memory. You're just rewriting to that memory. So, yeah, there's a lot of interesting stuff. I was kind of taking a look. I was reading this paper. I forgot what it's called. I'll just find it. But it was really interesting, and it's not something that's been implemented in a language before that I know of. But it's a different technique for garbage collection that seems beneficial for like certain types of programs, where basically there's no garbage collector running until you mark a function as like you can call it quote unquote like a arena or as a container, right? And all of the memory will get collected when the function is done. So this arena has a heavier cost during GC, but you get to mark what functions and therefore what they all that kind of stuff, and it kind of like, and they can't be recursive, can't be functions you call internally. So like if you have a main, that would all be arena because you don't want main to be recursive, even though it could in some languages. I don't know. It's like an interesting technique for like GC. And honestly, I was considering most of the stuff I want to use my language for, I don't need a GC. Like I'm not running it long enough. And if I do, I honestly really think my dream language would be C with the syntax for like interfaces, right?
Okay.
I think a language like C with interfaces is my dream language. I don't mind dynamic memory allocation. I want that low-level control, but I also really want interfaces so I can do composition stuff.
Interesting.
So like, I don't know. I kind of want to try. I kind of want to try that approach, like even for like a little toy project. So that's why I've been creating. Let's see, let me find it. Load up Little Linux. Oh wait, there we go. Let's see, projects. So in my custom Ling series, this is the code, by the way, that I was talking about in the Discord. So this is the repo that I would have everyone start with, pretty much, for the series if they wanted to follow along. But by the way, this is the syntax. I don't know if you've seen what expressions are. So, for example, to declare a function, right, it would be like fn or, func, and then let's say it's add. So it's add. And then what we can do is we specify maybe a return type. Let's say it's a float or F32, let's just say.
Okay.
And then we pass in the args. So each argument is going to be, for example, we do, let's say, X, which is a F32. And we'd have to do it like this. So it would be like, there's a lot of parentheses, as you'll notice. Y, X, F32. But what is really interesting about this is this is already in the form of an AST.
Oh.
Right? Function, this is like a function
Yeah, the function declaration.
declaration. This is the name, the return type. And then at the beginning of every parenthesis is the operation, plus, right? So you do plus 1, 5. That is an add operation.
Mm.
Here's how you would do prints. Print line, the args, hello. And then let's say I wanted to print like the sum, right? Sum is plus 45, 2, right? How would I then define this function add? So I do fn, add. And let's just say it returns an int. Let's just for now just forget about type checks, right? So x, y. And then here you would have your body. Right? So the body, this is a block statement, right? So this can be called block. And you notice how this is a AST, right?
Yeah.
This is already in the form of an AST, so if I want to do return, I just do return x, or
That's smart.
plus x, y. There we go. And then if I just want to call add, right, I can do print line results equals, and then I can just do add 10, 20, right?
Hold on 1 second. Sorry, my sister walked in.
You're good. So, like, say I wanted to create a structure called vector, right? This is what it would look like. I would have a field of x, and maybe the type of floats, right? I would have a field of y, and a, let's say a float, right? And then this is it, right? It's already in the form of an AST. This would be your member. This would be your member. For type stuff, right? And you can say this returns a integer, a float. An x, instead of being like this, takes in a float, or x, float, y, float, and there we go. Now it's all types. So it's a language, in fact it looks very similar to this. Or let's just do .scheme.
That is smart with the syntax of it.
Well, yeah, what you can then do is you can, for example, say you know what you want, you don't know what your syntax you want your language to be, but you want to work on your language, right? This is it. In fact, this is the entire parser. I just combined the lexer and the parser together, but, right, here's the tokens. That's it. Right?
Yeah.
Here's your lexing stuff. Actually, it's going here, right? And then token stuff. That's it. I mean, again, it's so basic, right? In terms of that. But anyway, this is what I was thinking of maybe starting this project off. So we just start building the parser just right here, right? Like,
I think that would be a great idea, because that's what you mainly want to focus on, right? Is that aspect
I mean, I
of it?
really care about the runtime aspects. I think that's the most important stuff. But you can see how, like, right, when we build the parser, there's only a few types of nodes. There's what's called well, first there's what's called a atom, which every language pretty much has the lowest denominator. In this case, an atom is a string literal, a number, or a identifier, right? Would you agree? Add is an identifier, a number, or a string literal. That's it.
Yeah.
Then you have what's called a list, which is, well, a atom followed by more lists. Actually, really, a list is just a list containing lists. That's it.
Yeah.
Or an atom. That's it. And this is your entire freaking AST.
That's nice.
This is it. Like, an atom is a string, a number, or an identifier. What's a list? Well, it's open paren followed by... Oh, no, it doesn't go like that. Sorry, I screwed this up. There we go. This is what a list is, right here. In fact, I think this is the exact BNF grammar, right? Like that, and then this would be... There we go. That would be it.
Huh. That's really nice.
A list is an open paren followed by an unknown amount. It could also be empty of lists or atoms. Right? And this is what this is what this Lisp language looks like. It is everything as a data structure and code. So something like this, you could say var foo, or let's just say var numbers. And then we can do vector, or like, let's just say list. And then just do 10, 20, 30, 40. Boom.
Huh.
So we're saying var numbers is a list. And this list might be equivalent to like a macro, right? Like in Rust. Or this is also a list, right? So this is data, but this is code.
Oh, that's interesting and confusing, but cool at the same time.
Yes, the entire language can be modeled through here. But this also means, right? This is a variable. This, you could take this and in any language, parse it. It's already parsed, right? It's already in AST format.
Yeah.
You take this, and all you have to do when you're building your interpreter is you already get this array, right?
Yeah.
Like in JavaScript, you can think of how this could be listed, right? This code, let x equal 45 minus 45 times 2. This code would be this. Let x times 45 2. That's it. Right?
Yeah.
Which means you just have to build a thing which takes this stuff and just translates it. When you find an open paren, time to create a new array. It's basically that simple. That's what makes Lisp super and every AST node can. It's been proven every AST can be translated to a list, an S expression like this, and vice versa. So this is a portable form for an S expression, which conveniently can also just be your language's syntax.
Huh. That's cool.
So here we have let x equal 45 times 2. And what's cool is when we get to evaluate this, right? Say we're given a list, right? We have this eval function, which takes in a list. Well, all we have to do is do what is the operation. Boom. Now we know what the operation is. The operation is always the first argument in the list. It's kind of like this is saying this is a variable declaration. This is a function declaration. This is a structure declaration. This is a field, right? So here we have the operation. Cool. So now we know how to parse this operation. So it's kind of cool. Like if we could like switch over the operation, and let's say the case is it's plus. Let's just say plus. Right? Here would be the binary code. We would then do const LHS equal, well, we need to eval the list at 1. And const LHS and then we have those sides, and then we just return the like that kind of thing, right? Or if this was code generation, right? We already have our thing, and it's no need to like, I don't know. Like it also means you can create a plus function, right? So you can imagine how you would create a function for let parsing. You would create a function for all those, and all you'd have to do then is kind of like a what's it called, a parser for like operators, right? You can create an array or a map that takes in the operator to a function that compiles it, right? A compiler function. So you can imagine if I say, hey, what is the lookup for plus? And then I just call it, right? And now I'm parsing plus functions. Or what if I parse let?
Yeah. Huh. That's cool.
So you can say, like, you can build a couple functions that parse let expressions, functions that parse that. And instead of having to have a switch case, you just basically, kind of like the operator precedence parsing, you just say, hey, I'm parsing a let expression. And what's cool is you don't even need to build an API if your language is already in the form of one.
Yeah.
In fact, I'm pretty sure, I actually bet you ChatGPT could build one because it's so little code. Wait, where's ChatGPT? Oh, I don't have it. ChatGPT.
That's cool, though. I'm excited to watch and learn from this series.
Yeah, I think it'll be... I mean, I'll just have basic, you know, makefile. I'll build the Lexa route so it's nice and error-prone. You know, basic little comments if people want help. Plus, I've already built Alexa in multiple series. One was a live stream where I built I think it was in like an hour and a half or whatever, in JavaScript. Which I think I did. JavaScript. Just learn how to do that. You can videos.
Yeah.
Plus, I think Lexing is the most boring part of it all.
I would agree. I really like the parser part.
Just parsing? I hate parsing. It sucks. It's so annoying.
It's fun. Because that's... I don't know. That's where you develop like the actual grammatical syntax and of the language and everything.
I think that parsing is fun, but I really think the most fun part of it all is the actual runtime, like compiling.
I could see why.
I'm gonna cry if they can't sign me in.
I just use my Google account.
Huh? I have it. I'm like, why is it telling me I have to publish for a split second? But...
There you go. Yeah, I've been the crafting interpreters book is really, really good. I'm glad you told me to read it pretty much, and gave it to me as a reference. It's great.
Yeah, it's a good one. It's pretty good. Let's see. We have ChatGPT. In C++, write a basic parser class which accepts valid as a string and translates it into AST. Let's see it. I have faith in you, ChatGPT.
This is version 4, right? I haven't messed with version 4. Yeah.
Oh. Yeah, it's Silicate, right? Hey, if you found an open paren, it's time to open a list.
Oh, that's cool.
Yeah, I'm parsing data. So I'm gonna try it. I have faith in you, ChatGPT. Don't let me down.
Oh, were you ever able to set up Neovim? Or not yet?
Nah, I gave up.
That's
I'm
fair.
happy with this. Good. After all, who knew?
That's fair.
Think of that. 55 lines. Let's see if it works.
No errors, too. Impressive.
So yeah, this is a node.
Okay.
Okay, so it could have done the 2 nodes, right? It should be a list versus an atom. I don't like that. I'm gonna see if it works, and then I'm gonna ask it to fix it. So let's do G++, dash O, main. Oh boy.
Nope.
Ooh, C++, you had one job. One job. Your code don't work. Gotta give it that constructive criticism.
Oh, yeah.
Okay. I apologize for the confusion. It was oversimplified and incorrect. Yeah, no shit.
I did use so I used ChatGPT to write me an essay for a class. I got an 88 on it. It was great.
Well, I've had it help me with like some of my computer organization crap, like SR latches and one of the most complicated algorithms I think I've ever had to implement. Is so cool but so fucking annoying. It's called Hamming codes.
Oh, Hemming codes? I watched a video on that. That's really interesting. Way above my head, but really
cool.
Interesting.
Yeah, it's pretty cool. So, in fact, one second, let me actually find the thing. Like, I'm not gonna lie, this is probably the cool. Even though, like, God, it's so hard. I think it's super exciting if you like. I bet you electrical engineering students would really like it.
Yeah, I would remember I was sitting at lunch watching it, and it was super fascinating. Let me see if I can find the video.
Yeah, because every position covers every. It covers, for example, the first bit, the parity bit, the first one covers all of the bits in the code, or all the bits in the message that have a 1 in the zeroth place, right? Which is every odd number. Then the second bit covers all the ones every 2, 4, 6, 8, etc.
Yeah.
And then like it's really convenient because if you mix and match, it can. So say you have a message of 10 length, right? That means you need 4 parity bits, which means all this stuff's fresh in my head. Don't worry, I'll forget it in the video.
Oh, this stuff is not fresh in my head. It was a couple weeks ago when I watched this video.
So like, you can find the parity bits, and then what it means is if you have 5 parity bits, for example, that means you have 5 bits. You have no clue, like. You have no clue what they are. But the convenient thing is it builds a system of linear equations that there's 5 linear equations solved with 5 unknowns.
Yeah.
And each of those unknowns, if you're given a message then, and you're given that linear equation, which the linear equation is easy to build because it's the same format every time, then you take that linear equation. In fact, here it is.
Ooh.
So here's the Boolean. Oh yeah, here's the De Morgan's law. But this is Boolean algebra. So you have something like y and x naught or x plus y naught. Exciting. And you'll do a lot of simplification, which is really annoying. Anyway, then you build truth tables. So from a truth table, you can then build that expression. And then from an expression, you can then build what's called K-maps or Carnot maps, which give you the simplest form without doing the algebra, which is nice. But they have weird rules. Like, this is a cylinder and a cylinder, so it's like a sphere.
Okay.
If you were to unroll this paper. And you have rules where, like, you can only build, you have to build the largest possible thing, but you can't connect, like, you have to have it powers of 2, but if you can form these, you get the smallest equation. So that equation up here can be rewritten as this.
Okay.
And then, what the fuck is this? K-maps are useful to find, simplest, blah, blah, blah. NANDs and NOR gates, now we're talking gates.
Yeah.
So given that equation, here is the circuit that maps this. But you'll notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's not 15 gates on here.
No.
Right? Because we were able to use a Carnot map to then make it look like this.
Ooh.
which is pretty nice.
That's
and then
nice.
here's more stuff. God, drawing circuits are so annoying.
They get messy quick.
Yeah. And then here's like a time series, so if you have digital circuit and stuff like that. Oh, and then here is how you compute the message for the parity bits. So it's just division in XORs all the way through. Good old stuff. And then we have, here's the formula to determine. So here's a 4 linear equation. This is for a message of 6 bits. There's 4 parity bits because the equation is m plus r plus 1. So this is a message of length 5 plus r, which is the unknown. That's the amount of parity bits you need. Plus 1 has to be less than 2 of the r. And then, so here's a message of 011001, which means bit 1 and bit 2, which you remember from the video, right?
Yeah.
Those 2 are always taken. And then here's a 0. Then bit 4, right? All powers of 2, if you'll notice, is taken for a parity bit. And then bit 8 taken. And then this is the linear equation. The unknowns are 1, 2, 4, and 8. Conveniently,